Hi everybody, I'm Mike Poland, the scientist in charge at the Yellowstone Volcano Observatory. Thanks for joining us today. I'd like to talk a little bit about what the Volcano Observatory is. What is the Yellowstone Volcano Observatory? What makes it up? What do we do? What's our mission? And also some of the neat results that we've come up with over the last few years. Some of the things that really make Yellowstone an impressive place to work geologically and volcanologically. Well, first I can tell you what the Yellowstone Volcano Observatory is not. We are not a facility. We are not a place. I think a lot of people, when they hear the term Volcano Observatory, they think of a place like the Hawaiian Volcano Observatory, where there's a wonderful facility that used to overlook the active eruption site at the summit of Kilauea Volcano. Well, the Yellowstone Volcano Observatory is a virtual observatory. There is no physical facility for the observatory. So we don't have that building like the Hawaiian Volcano Observatory, the Cascades, Alaska, or the California Volcano Observatories. Instead, we exist in a virtual space. Another important distinction between YVO and the other volcano observatories in the United States is that YVO is a consortium. We're a grouping of institutions. Now, in most volcano observatories, the US Geological Survey, where I work, is the main player for the observatory. There are some partners in them, but the USGS really is the main contributor. The Yellowstone Volcano Observatory is a consortium of 9 different organizations that all together work to make the observatory what it is. That includes the 3 geologic surveys of the states that border Yellowstone: Idaho, the Montana Bureau of Mines and Geology, and the Wyoming Geologic Survey. Of course, the National Park Service, which is Yellowstone National Park, the University of Wyoming, the University of Utah, and Montana State University, and then UNAVCO, which is a nonprofit research group that operates ground deformation monitoring equipment throughout the western United States. So it's these 9 institutions together that make YVO what it is. No one institution runs YVO, although the USGS has the responsibility for putting out the hazard messages. But we all work together for the goals of YVO. Well, you may ask, what are those goals? Pretty straightforward. The first goal we have is research into what's happening at Yellowstone, into volcanic processes, tectonic processes, earthquake activity, and hydrothermal processes. We want to understand what's happening beneath the ground. The second is monitoring that activity, earthquake and volcanic activity in and around Yellowstone. And our third goal is education and outreach about Yellowstone's geologic past, geologic present, and potentially the future as well. So how do we go about accomplishing those goals? It's really rooted in monitoring the activity of the Yellowstone system. So I'd like to go now and show you some of the monitoring networks that we use to accomplish those goals. And the first is most obviously the seismic network. Now, probably you've all heard about all the earthquake activity that occurs in Yellowstone. In fact, there's something like 1,500 to 2,500 earthquakes per year on average that occur in the Yellowstone region. And all those earthquakes are detected by a network of about 46 seismic stations that are spread throughout the Yellowstone region, most in Yellowstone National Park. And a lot of these stations have multiple seismometers attached to them. So there's all of this seismic equipment that allows us to capture very, very small earthquakes. In fact, nowhere in the Yellowstone region could something magnitude 1.5 above occur and not be very well detected. And in fact, in some areas, the monitoring is so good that we can detect earthquakes with a magnitude less than 0. Which are incredibly small earthquakes. And this is what one of these stations might look like, a small seismometer buried beneath the ground, and that allows us the best signal-to-noise ratio. It reduces the noise as much as possible so we can really detect these small earthquakes. There's also ground deformation monitoring. There's a few different methods to do this, but our bread and butter in the Yellowstone region is continuous GPS. That's one of these stations right here, and we've got about 24 of these GPS stations spread throughout the region. Now, these stations have an antenna that receives the satellite signals mounted on a permanent monument that doesn't move. And so when the ground moves, that monument moves, and we can track that motion by looking at the position of the GPS antenna over time. And then typically there's some radio telemetry, batteries, the receiver, the electronics that make the thing work. So there's about 24 of these spread throughout the Yellowstone region. We also monitor water in the Yellowstone region. We look at stream flow, the amount of water that's flowing down a river or down a stream, and its chemistry. And these are some stream monitoring stations we have in the Yellowstone region, and here's one located on Tantalus Creek, which drains the Norris Geyser Basin. We can look at the amount of water that's flowing through. We can actually look at the amount of chloride in the water as well, a chemical constituent. Turns out that chloride is related to the amount of thermal input. And so by looking at the chloride in the rivers, we can actually use the rivers as sort of a delivery system for bringing the chloride to us. And by looking for changes in chloride, we can get a sense of whether or not thermal activity is rising or falling in the Yellowstone region. And when you look at all the rivers in the Yellowstone area, the major rivers, we can actually get a sense of where the thermal activity is occurring on the whole. The bulk of the chloride coming out of Yellowstone is in the Madison and the Yellowstone rivers, which is not too surprising. The Madison River is draining the upper, midway, and lower geyser basins. The Yellowstone River is draining the entire eastern and northern parts of the park. So we get a lot of chloride in those, less in the Falls River and the Snake River drainages because, of course, those drain a much smaller part of the Yellowstone system. We measure gases as well. There's a couple of different ways to measure gases. The most common is direct sampling. We literally put a sampler, a tube, or a probe of some kind into a fumarole, which gas is actively coming out of, or looking at gas as it comes out of the soil or out of a hot spring, and we capture that gas and then take it back to the lab for analysis to see exactly what's in it. We're also starting to work with continuous gas sensors, and you can see a couple of those here. This is an eddy covariance system that's capable of measuring heat output and also carbon dioxide, which is a major volcanic gas, and something we call a multi-gas, which is capable of measuring the concentrations of many different types of gas, especially the sulfur species, the sulfur gases that you can smell all the time in Yellowstone's geyser basins. Of course, we also look at the thermal areas themselves, and the best way to look at this in an overall sense is from satellites, remote sensing. We can see thermal emissions from space. Now, this is a nighttime satellite image of the Yellowstone region. Things that are dark colored are cool, and light colored areas are warm. So anything light colored in here is typically water, which tends to be a little bit warmer in color or warmer in temperature, and thermal areas. And we take the nighttime images because now there's no solar radiation. The sun isn't heating the ground, and we're picking that up as well. So this is really a nice map of the temperature of the ground surface. For example, we can zoom in on the Norris area, and you can get a pretty good sense of the hot areas in the Norris Geyser Basin by looking at this. Now, if you add up all of the thermal areas in the Yellowstone region using these satellite imagery, you can get the total output, the power output of the Yellowstone just from heat. It turns out there's 1.3 gigawatts of geothermal power output. And for those of you in my generation, you know that's more than enough power to send a DeLorean back in time to 1985. We can also measure the temperature of specific thermal features, individual hot springs and geysers, by inserting thermal probes into the runoff areas or into the features themselves to measure their activity over time. One of the places we've done this most comprehensively is in the Norris Geyser Basin, where we actually have a temperature monitoring network that's connected via radio to the internet. So in fact, you can see the results of this temperature monitoring network by going to the YVO website anytime and downloading the temperature data. Let me show you an example of one of the neat things we've seen with that. So here's our 9-station temperature monitoring network in Norris. We're measuring features like Steamboat Geyser and Echinus Geyser. This is the temperature record for Echinus during the year 2017. You can see there wasn't a whole lot of variation, a little bit of increase in temperature during the summer as you might expect, and then September and October we see wide ranges in temperature. Now if we zoom in on a single day during that time period, this is what it looks like. These really sharp spikes in temperature that are occurring about every 2 hours. This was a time period when Echinus came to life. It started erupting about every 2 hours. It did this for a few months, and then it went back to sleep. And as of late 2020, it hasn't come back to life yet. So this is one of these neat things we can see with these remote temperature probes that are communicating via radio back to the internet. You can download these data yourself anytime you like from the YVO website. All of these data are used to help us understand the hazards of the Yellowstone region. Now, the heat engine that powers the Yellowstone region, the reason we have all these hot springs and geysers, it's because there is something we call a mantle plume or a hot spot beneath the surface. It originates deep within the earth. It's an area of thermal upwelling and enhanced melting. And that melting source is relatively stable, but the tectonic plates that make up Earth's surface move across it. So over time, that hotspot burns through the crust, sort of like a blowtorch as you're moving an iron plate across the top of it. And the hotspot started about 16.5 million years ago back in southern Oregon and northern Nevada, and as the plate moved to the southwest, we saw a progression of volcanism in the opposite direction, to the northeast. So the oldest volcanic rocks of the Yellowstone system, 16.5 million years old or so, are here in southern Oregon and northern Nevada. And over time, they get younger and younger and younger until we get up to modern Yellowstone. Now, the Yellowstone system now is composed of multiple magma chambers. We have this mantle melting anomaly deep beneath the surface. But there's a couple of magma chambers that this melting anomaly feeds. One's quite deep, 15 miles or so beneath the surface, and it's full of a very low viscosity magma called basalt. That's the kind of thing that erupts from Hawaii. Low viscosity, it flows very easily. In turn, that basaltic magma body feeds a higher level reservoir of rhyolite. Rhyolite is sticky magma, prone to be more explosive. And this sits about 3 miles. The top of that reservoir is about 3 miles beneath the surface in parts of Yellowstone. But don't think of these as gigantic magma bodies that are just full of roiling, boiling liquid material. In fact, most of this is solid. The upper reservoir is only 5 to 15% molten, and this lower reservoir here is only about 2 to 5% molten. So it's sort of a mushy, plasticky zone with little bits of melt in the middle. That's what the Yellowstone magma system looks like. And this is what drives the hazards in the region. Now, of course, the most well-known hazard are the big explosions, right? That's what everyone talks about. Everyone knows about the giant world-ending explosions. They're very big explosions, of course, not end-of-the-world events, but there have been a few of these that have happened in the last 2 million years, 3 of them. There was one that happened 2.1 million years ago, a smaller one 1.3 million years ago, and then 631,000 years ago, we had the formation of the Yellowstone caldera within the park. If that kind of thing happened today, of course, it would be very devastating to the central part of the U.S. We've done simulations on how ash would fall, and ash would blanket much of the U.S. This is probably what happened when this caldera first formed 631,000 years ago. But the chances of this sort of event are very remote. They occur once or twice every million years. The interval between these things is over 700,000 years between events. What happens more often are lava flows. And since the last big Yellowstone explosion, 631,000 years ago, there have been about 24 lava flows. And you can see them here in these different colors. The initial pulse of lava flow activity was 500 to 600,000 years ago. We had these orange bits of lava came out. And then there was another pulse of activity that occurred about 170,000 years ago to 70,000 years ago that gave us all of this pink-colored lava here. You can actually see into the guts of one of these lava flows by looking at the Grand Canyon of the Yellowstone, where all of this lava flow activity has then been altered by hot water moving around in the subsurface, and it gives you these spectacular colors. So lava flows, you might get, a few per 100,000 years or so. The area is full of faults as well, and this is because Yellowstone is on the edge of the western U.S. extensional province. We call it the Basin and Range. That area is being pulled apart by tectonic forces, so there are faults everywhere. All of these black lines are mapped faults in the Yellowstone region. If you got a lot of faults, you have a lot of earthquakes as well, and most of these earthquakes are very small, magnitude 1, 2, maybe 3. You don't really feel them. But Yellowstone, because it is this active tectonic area, can also generate some very large earthquakes. And in fact, the largest earthquake ever recorded in the Intermountain West, right outside Yellowstone. It happened near Hebgen Lake in 1959, and it was a magnitude 7.3, caused quite a bit of damage. In fact, caused a landslide that dammed the Madison River, resulted in the deaths of over 24 people, and created what's now known as Quake Lake, which you can go and visit today. So earthquake activity is quite significant in the Yellowstone region, and there can be strong earthquakes once or twice per century. That's perhaps the greatest hazard on human timescales in the Yellowstone region. And finally, we have hydrothermal explosions. There's so much hot water moving around in the subsurface in the Yellowstone area. When it flashes to steam, you'll get explosions. And there have been a dozen or so big explosions that have left significant craters, a few hundred meters across, since the ice melted about 15,000 years ago, the end of the last ice age. But there are also smaller explosions, things that you may have even witnessed in a geyser basin once or twice, so anomalously energetic geyser explosions. These happen almost once a year or so, mostly in the backcountry, so you wouldn't necessarily see them, but we also happen to see them in developed areas at times. The 1989 explosion of Pork Chop Geyser is a good example, or in 2018, Ear Spring, which had a rare explosion in the upper geyser basin. So this does happen from time to time, but they tend to be very, very small events. So that's the activity that we see in terms of hazards, but how might we characterize that? And I found an easy way to demonstrate that is to look at what's more destructive versus what's more frequent. And if we were to talk about those big caldera forming explosions, massive eruptions, those are very destructive but not very frequent at all, 1 or 2 per million years. And the last one was 631,000 years ago. A lava flow, not quite as destructive, happens a little bit more frequently. You might get a few dozen of those per million years. We've had a couple of dozen since the last big caldera forming eruption. Strong earthquakes happen much more frequently. They're pretty destructive, perhaps not as destructive as a lava flow, depends on their magnitude, but you can get 1 to several of these per century. There was even a magnitude 6.1 in 1975 right within the Norris Geyser Basin. And finally, you have these small hydrothermal explosions. The big ones you can get once every 1,000 years or so on average. The small ones you get more frequently, might even be a few every century that would be really noticeable. But those tend to be more frequent, but much, much less destructive than any of the other processes we've talked about here. So that's the hazards, that's how we monitor things in Yellowstone. Now let's talk about some of the neat discoveries that have been made in Yellowstone over the last few years. One of the coolest new discoveries in Yellowstone in recent years has been the identification of a new thermal area near Turn Lake on the east side of the park. You might have heard about this. It was recognized in satellite data. This is one of those nighttime thermal satellite images that I talked about earlier. If we were to zoom in on this area of the park, you can see these warm areas, the light-colored areas, and many of them are surrounded by these red boxes, these red shapes. Those are areas that the park knows about. They're in the park database. But look at that one right there. There was no red area around it. And a scientist by the name of Greg Vaughn, who works for the USGS and studies thermal satellite imagery, looked at this and thought, that's interesting. I wonder what that is, because it's not in the park database. So he grabbed air photos that have been acquired every few years of the Yellowstone region. This is that region. There's an existing thermal area, but the area he was focused on was down here. And in 1994, that looked fine. Well, here's what that area looked like in 2003. It's starting to look like there might be some dead trees in that region. 2006, well, there's definitely some areas here that are starting to look a little unhealthy. Well, there's 2009. Something has definitely changed in that region, and here we are in 2015. It looks like a full-fledged thermal area. You can see all the trees are dead. The ground has that white, chalky appearance, just like this existing thermal area up to the north. Sure enough, when we flew out to look at this, land on the ground and have a look at this area, it is a brand new thermal area. Trees down all over it, and there's that existing thermal area in the background. We can also look at this with thermal cameras. So this is a helicopter view, just a camera picture, and there's a thermal image. And you can see this very hot ground winding through the thermal area. And in fact, when we were on the ground examining this area, we found trees that were in contact with the ground were actually singed. Charcoal, they're carbonized in places. And when we put a thermal probe into the ground, we found boiling temperatures just a few centimeters beneath the surface in some of these hottest areas. So a very young, very vibrant thermal area. Here's another view of what it looks like from the ground, all these downed trees. There were even small areas of fuming, and we could find sulfur crystals in areas. So this is, we saw a thermal area being born right before our eyes over the last 20 years. This kind of thing must happen all the time in Yellowstone. And not only do thermal areas come, they go as well. Some thermal areas get cool, and you can actually see these when you drive through the park. Areas of chalky ground that are now cool, that used to be vibrant thermal areas, but no longer are. But in this case, we got to see one literally come out of the trees. Really an amazing series of observations. There's also been a lot of effort put into understanding geyser activity. This is some really neat work done by the University of Utah. During one of the park closures in November, they deployed seismometers all around Old Faithful. And when they looked at the seismic noise that was coming from Old Faithful, that's mapped out in this plot here, they could actually see water boiling beneath the ground. So each one of these triangles is a seismometer, the star is Old Faithful, and they're backing out the location of the noise source that they see with all these seismometers. I'm going to play a movie here, and minute 0 is when Old Faithful erupts. You can see it gets very shallow, and when minute 0 hits, bang, that water goes down low all of a sudden. So then it rises, gets up closer to Old Faithful again, get close to an eruption, the eruption happens, bang, back down again. So you can actually see the hot water rising beneath Old Faithful using seismology. This is really exceptional work done by the University of Utah crew. And of course, we can't talk geysers without talking about Steamboat Geyser. Steamboat has been extraordinarily active over the last few years. It does this. Sometimes it's very active in the 60s and the 80s and now. Between those time periods, eruptions are very rare, maybe once a year. And we can detect these eruptions in a variety of ways. Here's a seismic station that's sitting in the Norris Museum, and this thick signal right there is an eruption of Steamboat Geyser. These data are online. You can see them anytime, so you don't actually have to be there to know that Steamboat erupted. Now, we've seen a lot of eruptive activity, so 32 eruptions in 2018. We had 48 in 2019, and so far, as of November 18th, we've seen 44 eruptions in 2020. So Steamboat's remaining as active ever. At some point, it's going to go back to sleep, but so far, it's really putting on quite a show. There are other ways to detect eruptions of Steamboat as well. Remember, I mentioned that Norris monitoring network that looks at temperatures of thermal features. Well, here are the data you can find on the Yellowstone Volcano Observatory website for Steamboat. This is for a time period in December of 2019. All of this activity is temperature fluctuations due to minor geyser eruptions of Steamboat. And then they culminate in a major eruption, and then the temperature drops. And we see air temperature through this time period here. Basically, the geyser wasn't doing anything. And then minor activity picks up, bang, another eruption, and it drops back down again. So we can actually monitor eruptions due to the thermal signature we see in the water that's coming out of Steamboat. All of that water goes into Tantalus Creek, and we can see surges in the amount of water coming past our stream gauge on Tantalus Creek whenever Steamboat erupts. Here is the amount of discharge coming through this Tantalus Creek stream gauge, sorry. There are these huge spikes every time there's a Steamboat eruption. So about 90 minutes after Steamboat erupts, all this water flows through the Tantalus stream gauge. So that's another way to keep track of what's happening at Steamboat. You can see multiple ways of tracking eruptive activity out there. Now, Steamboat's been erupting, of course, very frequently since 2018, spectacular activity. And this is a wonderful photo that was provided by my colleague Jamie Farrell at the University of Utah from a helicopter. There's a Kindness Geyser down here. Steamboat is located right in here. And you can see all of this sort of dead or silica-coated vegetation. That's all of these eruptions have pumped out so much silica-rich water that it coats the trees. It's killed the trees or coated them with like a silica mud. And if you've been unlucky enough to have been parked in the parking lot when Steamboat erupts, your car might have gotten a healthy dose of this as well. Now, the same scientists at the University of Utah have done a really neat job putting out seismometers to look at Steamboat eruptions. Here's the Steamboat right there. There's Cistern Spring down here. All of these red dots are seismometers they put out to look at this. And I want to show you data from two, from one right next to Steamboat and from one near Cistern. This is showing sort of the noise that we see from the Steamboat area and from Cistern. And there's an eruption right there. And you can see right after the eruption, we see bluish colors, low levels of noise at different frequencies. A day later, you've got this sort of high level here, but not much happening at Steamboat. Then it stops at Cistern, but picks up at Steamboat. That sort of picks up again at Cistern. That continues for a couple of days, builds in a bit of intensity, and then, bang, we have another eruption. And right after eruption, that noise goes away. So we might be able to predict Steamboat eruptions by looking at the seismic activity beneath the geyser. This is brand new information that the University of Utah has collected, but perhaps this could lead to a way to recognize impending activity at geysers where we have a hard time predicting them, that aren't as regular as Old Faithful. So really exciting stuff. And I think this really demonstrates what I find so compelling about Yellowstone. It's dynamic. It's always changing. It's an amazing place for change. And it's never the same way twice. It's never the same experience twice. Geysers erupt differently. They come on, they turn off. Thermal areas come out of nowhere. It's an amazing place for that regard. So there's obviously a lot to know about Yellowstone: volcanic activity, earthquake activity, hydrothermal activity, geyser activity. If you'd like to know more, I just wanted to share a couple of places you could go for more information. One is the YVO website. And in particular, on the Yellowstone Volcano Observatory website, you can find something called Caldera Chronicles. Now, this is a weekly series of articles that scientists from YVO write about some aspect of Yellowstone geology or history or recent events, recent activity, recent research. It comes out every Monday, so you can check out Caldera Chronicles for some new tidbit about Yellowstone volcanology, earthquake activity, some aspect of Yellowstone's geoscience richness every Monday morning. You can also find annual reports online. We're trying to put together the activity that occurred in every single year into annual reports that describe how many earthquakes there were, what the ground was doing, was it going up or down, what kind of geyser activity was there, what kind of research did we do. So you can find that online in a series of free reports, one for every year. We also do monthly video updates to complement our text activity updates. We thought this would be a good way of really connecting with people. Hi everybody, I'm Mike Poland, the scientist in charge of the Yellowstone Volcano Observatory, and I'm coming to you today from the Upper Geyser Basin in Yellowstone National Park with the activity update for October of 2019. In these activity updates we can talk about what's happening in terms of earthquakes, point out where earthquake activity is occurring the most, how many earthquakes occurred in a given time, what the biggest magnitude was. We can look at deformation, GPS data for how the ground is rising and falling. Look at different places where that's happening. We can even look at eruptions of Steamboat Geyser, say. This is our real-time temperature graph from Steamboat. Talk about the eruptions that we've seen. And we always end our presentation by saying you can contact us for more information. And that's certainly true. You can give us a contact anytime you like. You can write us with any questions you might have, any observations you might have. Anything you'd like to know more information about, we're always there for you. So drop us a line and we'll do our best to help you out. And of course, we're also active on social media. The USGS Volcanoes has Twitter and Facebook, and all of our partner institutions, like the University of Utah Seismograph Stations and the Idaho Geologic Survey, have Twitter, Facebook accounts where you can get more information. Well, that's all I have for you today. Hope you enjoyed it. Hope you found that informative. And if you have any questions, remember, you can always drop us a line by email or on social media or however you like. Take care, and hope to see you in the field sometime.